All right. So, Mark, we've talked a little bit about some of the initial steps and considerations in the design of a CIP system. I want to talk a little bit about spray patterns inside of a tank and how you make sure you get good coverage. How do you start?
So, so the first thing you would do is you want to pattern within that vessel your spray pattern. So if you think about all of the occurrences that you have on a vessel, you have the manway, sight glasses. Certainly, biopharm vessels are going to have a lot more equipment and instruments, and each of those connection points, they can be really difficult to clean. And then also think about all of the different things you might have protruding inside of a vessel. Maybe you have a no foam inlet or a guided wave radar rod, something like this. So that's the reason why you pattern it. And to pattern it, this really starts to get a little bit into validation. And certainly this is where I would ask that your group participate in this. And I know that your group is done a number of these very successfully. So I would start with a riboflavin test. The riboflavin, of course, as you know, you spray this fluorescent substance within the vessel, and then you clean it. And when you're done, you shine a black light in there to see what you missed or you don't miss. And so I mentioned something about the spray balls. The spray balls, if you've seen one, they have these multiple hole patterns, and those holes are specifically designed so that they shoot a stream up towards one place or another to clean those difficult to reach places, at the same time while being fully drainable. And you think about the guided wave radar that we mentioned, a solid rod that's in your tank. If things aren't properly patterned, you're going to have, as that spray hits say a rod within the vessel, it's going to create a background where it's called the shadowing effect, where you won't see CIP coverage. So those are the things that that's one of the things you start with, is to make sure that you have full coverage, whether it's spray balls or impingement device.
Absolutely. And you talked about spray balls. Any other kind of spray devices that you would recommend or that you've seen commonly used?
So impingement devices, some will call them or spray clean in place machines, and they have a rotor. Some will have a rotary or planetary gear in them, so that they give a 360-degree turn in one direction while at the same time oscillating in another 360-degree pattern. So those are very aggressive, and depending on what device you're going to use, whether it's an impingement, as we're talking about, or spray balls, you need to make sure that you calculate your flow rates accordingly, because they are considerably different. The impingement devices use less flow rate, but then they use higher pressure. So those all play a role in your design of your overall system. So, and then, of course, throughout any of this, we want to make sure that we, include the elements of what you're doing when you start to design a system. You really need to know what your substrate is that you're cleaning. We haven't really talked about that a lot, but in most of the biopharm, you're going to be 316L substrate being the material of your vessel or your piping. And generally, you would take the worst case product that you may have and soil a coupon of it to the same substrate, and not only the same material, but the same surface finish. And then you would contact your chemical provider, because at that point, you're not quite certain what you're going to need for whether it's a caustic or an acid. And that chemical provider will do coupon studies using that substrate coupon that you sent them that's soiled, and they'll help you determine what type of caustic or acid solution and your temperature. And that, of course, leads into what we call tact time, or tact within CIP. So TACT is an acronym for time, action, chemistry, and temperature. So you derive those elements out of those coupon studies.
Well, you derive those elements out of the coupon study, but what does that lead you to? What do you do with all that information? And you've looked at your pipes and your valves and your dead legs. You've done all of the studies you need to make sure you've got good coverage in your tank. You've done all of your tact where does that take you then?
So the three most important factors when you're cleaning anything, with a clean in place system are dissolution. Being dissolution, first of all, are you able to dissolve the soils? And that's going to come out of this study that you've just done with the chemical companies. They're going to help you determine if you are able to dissolve it, and if you are, what are you going to need for chemistry to do so, in temperature and the action, how much pressure you're going to need to do that, and how much time. So given that not everything can be dissolved, if that's the case, then you have to find a way of dislodging it. So that's the second most important factor in cleaning, is dislodgement. So maybe you have big chunks or something that just won't dissolve, but you want to at least get them broken loose from the surfaces and dislodged. And at that point, then the third most important factor is suspension. So whether you dissolved it or whether you dislodged it, you want to make sure that you keep it in suspension throughout that CIP, with its CIP fluid, so that you can remove it from your piece of equipment that you're trying to clean.
Do you have any tools to help you verify without having to go through this physical iteration process to determine all of this?
So at Design Group, we start out with hydraulic modeling. And hydraulic modeling is it's a really effective tool where we can enter all the parameters of what the substrate is, what type of piping material you have, and then and what we do is we calculate basically the pressure and the flow rates that we need to create not only turbulent flow, and we can verify our losses that we might have through, say, friction loss, because there's always friction loss when you're running anything long through a pipe. That'll slow it down. So we want to make sure that we calculate those, and probably most importantly is that we have a balanced system. So one of the things with CIP, if you're sending fluid out to a CIP, you're trying to clean maybe it's a bioreactor at 30 gallons a minute, you want to make certain that you're able to at least get that 30 gallons a minute back, if not more. If you're not able to, then you're going to have pooling, possibly within your vessel, and that pooling is going to result in what's commonly called the bathtub effect. Same as putting a dirty child in a bathtub, and then you drain the bathtub and you got a ring in there. And the same thing will happen with your tank as well. So these are really important considerations, and all this plays out when you do a hydraulic modeling. So maybe you have a restriction point at the exit of your vessel. Maybe your vessel harvest valve won't allow you to get the volume of fluid out that you need. And then from this, you can derive that, hey, I need to do pulsing. So maybe you pulse your system so that maybe a different flow path is seeing continual flow, but the vessel's pulsing so that it has time to drain out and not create that bathtub effect. Yeah.
Excellent. No, all good considerations and things to think about. That will lead us into the last section. So I appreciate your time, Mark.
Oh, thank you. It's been fun.